Hello, my name is Yaejoon Jung, and today I'm going to be presenting my research, designing a novel bamboo-inspired lattice structure for 3D printed total knee arthroplasty implants, using FEM and ML-based optimization approach for advancing public health and surgical equity. Before my presentation, a little bit more about myself. I'm a rising junior at Phillips Academy Andover in Andover, Massachusetts. I'm very passionate about biomechanical engineering and rehabilitation. I'm also a research intern at the Northwestern University. Apart from class, I'm the co-president and the co-founder of Phillips Academy Paper Exploration and Research Society. I'm the board member of Science Olympiad Club, senior board of Anatomy Surgery Club, and associate editor of the Science Tech Review. I'm also a very avid runner. I did cross country and track for more than 10 years. I ran the Boston Marathon, and I enjoy coaching the Special Olympics running team. I'm also a professional digital music producer. Now, I'll move on to my presentation. Osteoarthritis is a chronic condition where the knee cartilage wears down, causing pain, stiffness, and ultimately hinders one's mobility. Luckily, there is a solution to this. It's called TKA, or total knee arthroplasty. TKA is a surgical procedure that replaces the damaged knee joint with artificial implants, usually titanium. Yet, the current limitations of TKA, lack of personalization, wear-in complications, and frequent repair of implants are all current concerns. One really promising solution is personalizable 3D printed TKA implants. To create this, you have to stack these small structures called lattice structures on top of each themselves. However, the material properties are largely dependent on the lattice structures themselves. And also, testing each design one by one takes a lot of time, resource, and energy. This was the challenges that I faced about 8 months ago. Alongside that, I was asking myself, how can we make a lighter, more durable, and more biocompatible lattice structure? How can we do it faster and at a lower cost for the increasing elderly population? In this study, I choose a combination of bamboo-inspired design and FEM and machine learning-based approach to design a novel bamboo-inspired lattice structure that is not only more durable, but also lightweight, has better osseointegration abilities for the elderly population. First, I started by creating the lattice design space. I was inspired by the hollow cross-section of the bamboo and its lightweightness, and also the nodes that stand vertical stress. Extracting these key features, I create the lattice structure and the cell. On the right side is the design space. I create the lower and upper boundary so that it's conducive to osseointegration. If we were hypothetically dividing it into zero point 0.1 increments, there would already be 12,000 combinations possible. This is realistically impossible to create and simulate one by one. I overcome this challenge with two revolutionary solutions. First is a finite element method simulation. By using these material properties, I was able to simulate how a TI-6804V of this structure will react under vertical stress conditions. Second, I used a machine learning-based approach. I had a goal of normalized energy absorption, which is characterized by energy absorption over packing density. This was intentionally created to capture a structure that is not only more strong, but also more lightweight and has better porosity. I conducted this study with Gaussian process and the Bayesian optimization. Here are my results. First, I generated 20 different lattice structures using Latin hypercube sampling, and each of them would undergo a sample analyses. Using the data, I first conducted a Gaussian process regressor. I used 16 of them to train the model and then 4, as indicated in this 4 blue dots, to test the model. I obtained the R-square value of 0.803, which was deemed sufficient enough to use as a baseline estimator from a Bayesian optimization. On the right side, the normalized energy absorption of the Bayesian optimization continuously increases until it converges at about 800 megajoules per meter cubed. This is a significant 70.69% increase compared to the mean of the normalized energy absorption of the train set before the optimization. Additionally, the packing density converged to 0.48. This is clinically really significant because 0.48 is within the porosity of the nearby bone, making sure that it has better osseointegration abilities, as well as making it a lighter TKA. Through the GP regressor, Bayesian optimization, I was able to create the optimal lattice structure as displayed in this slide. I also did a validation study. Using 3 points that the machine learning model hasn't seen before, I still obtained a R-square value of 0.85. This confirmed that the research process, the design process, machine learning, and the validation were all really accurate results. I also conducted a SHAP analysis. A SHAP analysis shows which features were crucial in contributing to maximizing the energy absorption. I was able to figure out that higher diameter in the middle, thicker node width, as well as lower overall height all contributed to maximizing the normalized energy absorption. This key insight can be used in other studies as well in the future. Now, implications. First, by using this lattice structure, we can create a more durable, stretch-resistant, and lightweight TKA. Second, we can decrease complications regarding biocompatibility. Ti604V is inherently a biocompatible material, so by using this, we can decrease the amount of side effects and complications regarding putting a metal implant into your knee. Third, we can create a TKA at a lower price point due to reduced material usage. As mentioned in my presentation, this lattice structure is very porous. Since we use less titanium, which is really expensive, this TKA can be produced at a very low price, ultimately making sure that it's available for all socioeconomic classes. Fourth, by conducting the study within 50 FEM simulations, I conduct a new way of fast and efficient lattice structure development that can be used in future studies as well. Now, how can this small lattice structure be implemented into real-life applications, clinically, and also just in people's lives? Well, first, you can expand access to TKA surgeries in underserved areas because it's very low price and it's easy to produce. Second, you can reduce healthcare system burdens by minimizing the frequency of TKA redesign. Since this TKA is really durable, it can naturally decrease the amount of frequencies that people have to go and fix their TKA implants. Third, wider global accessibility from open source 3D printing is possible. So what this means is that people not from metropolitan cities, people in rural areas can also access this TKA implant, regardless of their geographical location. Last but not least, scalable and affordable TK to support increasing numbers of elders in the society is really important. So that is also a crucial benefactor. For elders, maintaining connections, movement, and going places they want are crucial for their physical and mental well-being. Through this research, I hope to maintain that and make sure that the rest of their lives are also happy and flourishing. Here are the references, acknowledgements, and thank you for listening to my presentation.